my pleasure to introduce Grigori Chapiro from Federal University of Rio de Janeiro in Brazil, in Minas Gerais state. Actually, the part of Rio de Janeiro.
Nearby.
So today is talking about traveling wave solution describing combustion waves in porous medium.
Thank you very much. Well, continue a joke. It's always a pleasure to come to this small neighborhood of Juiz de Fora called Rio. So, so first of all, I want to follow serious idea, and I was a master and PhD student with Dan under Dan's supervision, and well, he continued.
How could you stand it?
Well, I continue under your supervision for this past year, so I think after some time you like it. Strange at the beginning, but wait. Anyway, I will talk about this work of traveling waves. I try to make some Frankenstein presentation here, but hopefully it will work. So this is part of the work with a lot of people. Lucas Furtado came here for a while for internship in IMPA. Dan Marchesin, of course. Fatih Özbak made his PhD under supervision of Stephen Schechter from North Carolina University. Now he's working in Haran University in Iran. Yes, in Iran. Actually, I was really surprised. It's very close to Syria border. Well, anyway, so Laura, Turkey, Iran, Turkey. Turkey, but very close to Syria border. This is still correct. Laura Sianos is a colleague of mine, and recently, so the student, my master student, Rosemary, she is interested in this work, and hopefully she will continue. Well, first of all, we talk a lot about Riemann problems in this meeting, but when you want to solve viscous profile for shocks, it's a small diffusion appear here, and one of the forms of analyzing it through traveling wave solutions. So traveling wave solutions, it's basically here. So you consider instead of variables x and t, you change for xi and t, where xi is a traveling variable, which is x minus vt, where v is a constant speed. And this PD transforms in this one, and then you look for stationary solutions. So basically, this red term, you take it out, and then you have an OD, and this OD represents a traveling wave solution. And we are looking for existence, uniqueness, stability, and so on of this type of solutions. So there is a nice book of 3 Wolperts about everything about traveling wave solutions. Well, Dan starts with a long time ago. So this is the first paper of singular perturbation applied to this type of problems I know. And but I will concentrate in combustion theory. So this is a famous picture. I will not talk much about it, but I think I presented here in IMPA this picture like 10 times. So, okay, let's skip to another one. So our model is.
For me, it's new.
Okay, so we are.
I cannot find them.
Yes, well, it's not a. The conference is not complete without this picture, at least, yeah? Okay, so we are injecting, so we have a reservoir, we are injecting oxygen here, we are expecting to produce some oil here. So we inject oxygen, make a combustion, and then the heat propagates forward, and the light hydrocarbons evaporate, steam, so water evaporates. Then you have a zone with all the chemical reactions. You leave behind some immobile coke zone, and this immobile residual oil, it's almost immobile. So that's why in this modeling, the fuel doesn't have mobility. And then we have a reaction, this combustion, so the combustion zone, and we are talking only about this red zone here. A little bit of brown and blue. So these three things here, we will talk in this here. Well, this is corresponding, this picture corresponds to high temperature oxidation. So for low temperature oxidation, Fabio's talk is more, it was closer. And of course, there is paper from Dona and Alexei about it. So our model is 1D tube. Yeah, we imagine the model is 1D. We imagine some sample or experimental design. The tube is full of this porous rock, full with carbon. Well, it's a mobile fuel. We inject air, produce combustion wave, and study how it behaves. So, of course, there is a number of papers about it. So when you're looking for traveling wave solutions, there are different ways to look for them. So one is making, well, I don't know if it's completely correct, Zeldovich method. So basically you take a combustion zone, you split it in layers, and you analyze differently the combustion in each layer with some particularities. Then you glue the solutions by hand, and you obtain the resulting solution. The problem in this method is that you treat a heat equation just as a C1 solution. So the solution of heat equation is C1. So for mathematics, it's a little bit strange. But it produced good results. So these 4 papers address this issue. I will not go inside each one of them. Then there is another possibility that we attack traveling wave solution as it is. So that just the OD solution like it appears from this so traveling wave solution, traveling wave form from PDEs, from balance laws. But then you cannot, the more realistic models result in quite complicated ODE systems, and you cannot address them directly. So these work with singular perturbation, and then you, of course, here you approximate traveling wave from one size. Here you approximate traveling wave by singular perturbation and asymptotic series expansion. Well, there is another way. So the other way is to analyze more simple model. So we simplify the model of combustion until quite simple one, but then we can prove rigorously existence of this type of solutions. So, well, I started participating from this work, and then we extended the result with my colleague Laura Senos to control flow case, and I will talk about these 2 papers here. We studied dynamics, stability, for the solutions with Lucas Furtado. And then there are some extensions, of course, of this work. One take into account thermal losses, and another one is just submitted. We generalize it to a little bit the partial differential equations. This was a result of Fatih's PhD thesis. So, following previous talk, we have a lot of hypotheses. We cannot do anything without them. So the flow is one-dimensional. Immobile fuel doesn't vaporize. Fuel occupies a small part of available space, which means that the porosity of the porous medium is not changing. Local thermal equilibrium, we have only one temperature. Constant gas speed, this of course is really strong hypothesis because we don't have partial flow and so on. Heat losses are neglected for this presentation, but we already extended somehow to where heat losses are not neglected. Pressure variation are small. This is connected with a constant gas speed. And of course, we have more 2 hypotheses, really strong ones. So this model considers that the speed of thermal wave and the speed of oxygen wave are the same. But so the thesis of Fatih, which I'm not going here, but we could prove the similar results for different speeds. And then really strong hypothesis, which is not physical at all, is this cut-off Arrhenius law, which means that so instead of considering temperature 0 Kelvin, which is no reaction, we take it out a little bit, so the reaction happens in some positive temperature. Well, this is dimensionless, of course. This is already prepared for mathematics. So please don't be afraid of negative temperature. It doesn't mean negative Kelvin temperature. It just means down some reference. So we have some reference temperature T, which can be 20 degrees, and then we are considering that below this temperature there is no reaction.
You still put it in the Arrhenius factor.
Yes, if you manage it correctly. So here it will be T plus T0. This will be correct Arrhenius. So this is a strong hypothesis. There is no T plus T0 here inside this function. Okay, well, why it is so important? Because with this, so this type of analysis, it's impossible to do with this term.
It's not reality.
No, this is not. This is mathematical model.
There's no model which is every reality, so there are all models are wrong, but some models are useful. But I really, as an engineer, I really, this temperature.
I agree with you. Correct. I agree completely with you. But so.
Put Arrhenius hat.
Huh?
Put the hat on top of the Arrhenius.
Well, we can actually put it like.
That's okay.
Yeah, it's not.
So
Yeah, I can put like the line like this. Yeah, red line. So no Arrhenius law. And then, well, okay. So this model.
I've had distinguished mathematicians, but this is really the limit.
Well, to my defense, we made some nice papers with correct Arrhenius law as well, but not so rigorous. So in the wave analysis, this system of PDEs possesses contact waves. Of course, the contact wave is, we call it contact for simplicity, and we indicate it like this, yeah? So the wave with speed c from one state to another. So the contact wave will have speed a, and we call it contact. However, you see that there is a diffusion here, so actually it's a contact wave in oxygen, and in temperature it's spreading a little bit. So in the simulations, I will not show them here it will take some time, but I continue calling contact. However, we know that it's close to. Well, and then, so we proved some theorems about the combustion wave. So there is two types of combustion waves in this problem. The fast ones, so what means fast? That this speed of combustion is greater than a, which is this contact wave speed. And slow waves, which means that CS is, it's less than A, yeah? That's why we call it slow combustion speeds and fast combustion speeds. And there is only 4 possibilities among all the 9. So the fast combustion speed can go from some state where there is no fuel to some state with low temperature, or from some state of no oxygen to temperature. We call it fuel control, temperature control, and oxygen control. So there are 3 possibilities for the final equilibrium states for this ODE. Well, and so basically this is principal theorem. So we show that there is a slow combustion wave and fast combustion waves under some certain hypotheses, which are useful. So if I summarize all the waves we prove, all the sequences, existing sequences in this problem are here. So zero speed waves are full waves, so they are, as full doesn't move, so these are contact waves but without any speed, so they're stationary. Then we have waves with A, which means these contact waves I explained before. And then we have some combustion, fast combustion CF and slow combustion CS. So this picture is trying to organize in the sense that the speeds are increasing, and here are hidden 22 different solutions. So we solved, in this sense, we solved all possibilities for the traveling wave, which means we solved all the possibilities for Riemann problem solutions.
Did you mention ODE before you were stating your main theory? Or I missed the...
Yes, sorry. So
I missed the ODE.
Yeah. So yeah, actually, this slide is missing, but so we are. But no, but in a sense that here is the ODE, because if you change, you just need to change. So traveling wave solution, it means that you change dt every derivative in t by minus v derivative in psi and x by psi. So and this is a system of ODEs.
It's simple to throw away the ddt and you have ddx.
Yeah, instead, no, change t by x with sign minus.
Okay.
And then it's a system of ODEs.
So change t into
I
x.
was missing the accent notation. Sorry, that's my fault.
No, yeah, it's my fault actually. Now I realize it will be better, but I'm trying to put everything in one presentation. And, okay. So yeah, we are trying. So we are trying in like this is the ODE, and we are trying to prove the existence of heteroclinic solutions connecting like alpha and omega limits equilibria. Equilibria indicated by these combinations of letters FC, TC, and OC. So this was a picture of the first paper I say we were to review. And there is a hypothesis here that all the combustion waves are positive with positive speeds. And now we extended this to negative speeds. So this was work with my colleague Laura. And we proved actually that there are two possibilities for counterflow combustion. We call it CC, of speed of counterflow combustion. And under similar hypotheses, however, the proofs are a little bit different. Of course, are similar, but not the same. We prove the existence of such solutions. So, and the same picture as before now can be enhanced, and here there is almost 40 possibilities now, because we add these counterflow combustion solutions. And now the Riemann, we have much more possibilities for the Riemann problem solutions. So I think Eduardo is saying me that I have no much time.
Go ahead.
Yeah, but so these are main results. So there are no possible combustion traveling waves of the system before with negative velocity except these two. And the next theorem is the existence of such waves. Well, I will give a very, very short idea of proving this. So we have, these are two equilibria. So this is minus and plus, or here theta is a temperature, rho is fuel concentration. So this equilibria, we have fuel, but temperature is negative. Please don't be afraid of it. And here we have positive temperature and no fuel. So this is a wave connecting low temperature to no fuel, yeah? TC to FC wave. And then we have some invariance here. And what we prove is that the wave have to be in the middle of these two manifolds, the red one and the blue one. And what we prove is that with some limit case, in this limit case they have this position, and another limit case they have this position. So just by uniqueness of solution of ODEs, there exists an orbit coming from one equilibria to another. Of course, these are 15 pages of demonstrations, but basically in 30 seconds I can make the idea behind the proof. Actually, we also addressed uniqueness in this work. We used this quite interesting work of Schechter from '87, and we applied Melnikov's integral, and in one, but however in Melnikov.
No, not here.
Oh. Well, and okay. Okay. Well, I'm sorry for that. But we only managed to prove that this integral is negative in one case, so actually we proved the uniqueness of solution only in one case. Okay, finally working with Dan showed me one very nice thing, that we have to go through and make very, very clean text to submit to some papers, and the text have to be perfect, but it's not always really easy. Well, thank you very much. Dan, happy birthday. Happy to work with you.
Thank you, Grigori. We have time for questions, comments, please.
Can you comment on the case where the velocity A and changes in the other equation to a B, and you mentioned the paper that you had in progress, or
No, actually, it's accepted already, but yeah. So
small a.
yep.
In the equation A.
Yeah. So here, physically, this doesn't make a lot of sense. A equal to this. Both speeds are equal. So when we change this to B, so the equations are similar. However, what happens is that in order to prove, so here OD is a second order OD. So when we transport it to first order OD, we have a system of 4 equations, which is completely impossible to work. We need to come to 2D phase space. In order to come to 2D phase space, we have 2 invariants. So we just notice that these terms are equal. You can substitute one into another, and you have 2 invariants. But to work with them, first we didn't realize how to work with this A different to B, but when they are equal, you can produce 2 invariants, and then you go down from dimension 4 to 2. So the proofs, how these pictures show, the proofs are in 2D, and then it's possible to do it. When the case is, when you took these letters, so A different to B, B greater than A, in principle, we have one invariant, clear, and another one was not so obvious, so it took some years to realize how to construct it. But then, when it was done, we managed also to come to 2D, and then the analyses were not the same, of course, but similar. And in this paper, in this Journal of Advances in Differential Equations, also stability with auto software were made.
The conclusions are also similar.
Are similar, however, so the result, what happens is that this waves continues, and here in the middle appears more 2 waves, which is middle combustion waves, middle speed. Because so you have A and B, and there is a possibility of combustion waves speeds greater than A and smaller than B. The funniest thing is, so the proofs for these 2 remain almost the same, but for here is completely different, because this solution takes some properties of here, some properties from here, and actually it appears one very strange hypothesis which we don't understand yet, but hopefully for mathematics you just put it like hypothesis. But from physical point of view, we are still struggling with it. Yeah.
Okay, Roger.
Can you say a few words about trying to remove the heads from
Arrhenius? Yes.
In other words, what's reality? A little better.
So the problem of trying to remove Arrhenius is the following. If you look here, we have this equilibrium far away from this axis. So the point is, if we use correct Arrhenius, then we have TC state will be exactly here, so for 0 temperature. And however, from OD point of view, there is this work of Schechter years ago, I don't remember exactly the year. So this is not hyperbolic equilibrium. And then, in order to prove this existence, the orbits have to enter it exponentially. So it's not hyperbolic, but the type of connection with the so not saddle, which is not hyperbolic saddle, it has to be almostly hyperbolic. The behavior has to be like hyperbolic. However, if you move this point here, it's not like that. So we cannot prove it. What happens actually in so in the first work we did using singular perturbation, we used correct Arrhenius, and then it appears a long tail for the solution. And this long tail, so today I understand that this long tail is because the orbit doesn't approximate equilibrium exponentially, which also doesn't, physically doesn't make a lot of sense, but mathematically this is the point, yeah? And when you move, so this distance, well, here of course is a plot, but mathematically if you move it 1 epsilon away, you have exponential connection.
Let me summarize. Either we do nice math or we do reality. We choose nice math.
No, I know that I'm really fascinated with this approximation and it works. I know that makes right, yeah.
But you're right, we have to do both. Otherwise, it's not justified. That's an important point.
Did I understand correctly that in all the cases you treated, even with negative velocities and so on, you were able to construct complete Riemann solutions
Correct.
for all data? Yeah.
Correct. Except, yeah, well, when I say correct, let me, so you see here, there are some hypotheses appearing in the theorem. So for all the other, the last case where I commented, when A different from B, all the phase space is not covered. There is a small, very small parameter gap. Numerically, in this gap, the solution exists. However, we couldn't prove it. So, this is really strange. But we're honest in a paper, so we put a hypothesis.
Okay, next, thank you, Grigori.
Thank you very much.